for the lines, it doesn't work, right?
Yeah, I
Yeah,
don't think
so for the lines, like the row of the column of like 4 dots, 5 dots, and more, I'm pretty sure it doesn't work because you could use a similar argument to what Lucas did last time for the 3 dots.
Right, which one doesn't work?
E, I guess.
E, you think none of these work?
Yeah.
Right, okay. Actually, 4 dots does work.
Oh, okay.
Wait.
Okay.
2, 3, 4, 5, 6, so then I'll consider this one. 2, 3. Okay, so 2 works here. Just going to it's here.
Got it. Yeah, 4 dots work something like this. Yeah, so another way of drawing it is just the 2 lines. And then yeah, that's it. Yeah. That's 4 dots. That one works. So did you think about 5? Or you didn't? Once you thought 4 didn't work. I think these examples, they show that this is a more difficult problem than you might think at first.
Yeah.
Anyway, perhaps you could think some more about 5.
Yeah.
I don't remember what the answer is there. So maybe you can. And what about F? Did you put some answers there?
I feel like each polygon has a construction because I feel like this is out of the blue, but if we consider the hexagon, it will kind of, if we consider and have the point at the center of a regular hexagon, we can make it such that its equilateral triangles are tessellate. So maybe we could use that for, although tessellation has nothing to really do with graph theory, we could use somewhat similar construction for all the polygons. So
Right. Okay, so what you're saying with, well, the one I didn't draw here yet, the hexagon.
yeah.
If we add a point, we get something like this with triangles.
Yeah.
And then we can tessellate the plane.
Yeah.
That's right. So let's see, something like this. let's continue. So we yep. What about the pentagon?
Pentagon.
Come up with anything there?
I feel like it's you use like the idea of the hexagon tessellation somehow to help aid the construction of all other polygons.
Well, that doesn't work for a triangle, does it? Because
Yeah.
we saw that actually, if we just add a center, then actually that's it. It's a complete graph. So we're not getting a tessellation of the plane there.
Yeah, that's fair.
With a square, let's think about the square. Right, you want to add a vertex here like that. Does it help if we draw it like this?
That's a pyramid.
Oh, that makes sense.
Oh, it's like a pyramid?
Also, not the hedron works.
What is it?
Like a pyramid.
Well, that's a pyramid. These only have 3 vertices. We have to add 1 more.
Yeah, so an octahedron.
Right. That's right. So we don't get a tessellation of the plane here either. It closes up. You want to guess now about, or think now about what the pentagon might give you? Perhaps I'll leave you to think some more about that one. Let's think now about the heptagon. So we get something like this when we add our center. And now the center now has 7 neighbors. If we look at another vertex here, this has 3 neighbors, and so we have to add 4 more. So this is your idea, isn't it? To try to use the same idea.
Yeah.
Tessellate the plane. 1, 2, 3, 4, 5, 6, 7. Something like that. And now this one has 4 neighbors, so we have to add 3 more. And now this one has 1, 2, 3, 4 neighbors, so we have to add 3 more. It's fairly clear that we can continue doing this.
Yeah.
If you think, let's just go back to these examples now. You try the same idea for the triangle or the square. What you find is that you cannot, when you try to keep adding more vertices, it's forced to close up. Right? It's forced to close up to the tetrahedron in this case and to the octahedron in this case. So the question now with the pentagon is this idea going to work so that we get some tessellation of a plane, or is this going to be forced to close up as well? Now the hexagon does it, we get a tessellation of the plane. The heptagon, it seems we can keep going. But there's going to be a problem, isn't there? Because with the hexagon, we get equilateral triangles. Each angle here is 60 degrees, and there are 6 of them meeting at each vertex, and 6 times 60 is 360. But now what are the angles on these triangles?
Doesn't add up cleanly.
Doesn't add up, no. So these in the tessellation, but not of the plane, but of what's called the hyperbolic plane. Right, the sum in the hyperbolic plane, the sum of angles of a triangle is less than 180 degrees. This is a non-Euclidean geometry. Right, so in Euclidean geometry, the angles of triangles add up to 180 degrees, but in this non-Euclidean geometry, a hyperbolic plane, they add up to something less than 180 degrees. So it works as a graph and as a geometry, but it's not the geometry we're used to. It's hyperbolic geometry. And actually, we can think of those as sitting on a sphere. Right, if we put this, let's just take the tetrahedron, say. If we put those on a sphere, so I'm not drawing it very well, but something like this. On a sphere, these angles add up to the angles of a triangle add up to more than 180 degrees. Just think of a triangle. If you put it on a sphere and you make the edges great circles of the sphere, then so a great circle is a circle that cuts the sphere into 2 halves. Right. If you think of take 3 points and then join them up to form a triangle with great circles, the angles there will add up to more than 180 degrees. So this is also a non-Euclidean geometry. It's called elliptic geometry. So we've got elliptic geometry and then plane geometry with hexagons, and then hyperbolic geometry for all the n-gons more than More than 6.
Oh, all of them.
Yeah, so all of them. Once we go beyond 6, we can continue this, but the yeah, but we get hyperbolic planes, not the usual Euclidean plane. So have you seen some of the pictures of Escher?
Oh, what's Escher? The hand drawing itself.
Yeah, so he's got some pictures of I think it's one with frogs, and there's something with different types of birds. So the tessellations, but they tessellate not necessarily tessellations of a plane, but of the hyperbolic plane. So some of his pictures are tessellations of the hyperbolic plane. If you have a look at those, you can see some examples of this. Okay, so that's those examples. But I guess we start to see now some answers to some of the questions. So in the case of the triangle and the square, it does extend to a vertex transitive graph, but they're not an infinite one. It has to be finite.
Yeah.
In the case of a hexagon, or an n-gon with n greater than or equal to 6, it extends to a vertex transitive graph, but it can't be finite. You can only get an infinite one that way. 5 we haven't answered yet. Now there's one thing you might wonder, well, can we, if you think about just 2 points, remember we looked at this example where we took 2 points and then we add a center. Well, that can extend to an infinite one, a line, or we can wrap it round it and make a polygon. The polygons all satisfy this. So this one, the line covers each of these by wrapping around. So you might wonder, well, what about one of these examples? Can we fold them up and wrap them around something finite? Well, that doesn't work either. There's a have you seen the result of Euler on the sum of the number of if we have something in the plane or on a surface of a sphere, the number of vertices plus the number of edges plus the number of faces. The number of vertices minus number of edges plus the number of faces is 2 or minus 2, depending which way. Forget which way it goes.
Yeah.
Right. So so that tells you actually we can't tessellate a sphere with hexagons. If you think about it, that tells us we cannot tessellate a sphere with hexagons or heptagons or anything higher. So we can't, unlike the one-dimensional case, we can't take one of these 2-dimensional tessellations and wrap them around something finite. That doesn't wrap them around a sphere. That doesn't work. Okay, so that's those examples. I guess we've still got these two with a 5 to think about. The pentagon here and the 5 line. But that's those examples. So I guess you've got a few things to think about. You can look for these pictures of Escher and think about tessellations of the plane. Maybe something on hyperbolic geometry. You can see why Euler's theorem tells us that we can't wrap the plane around a sphere. but then there are other examples you might want to think about. Thought about any other examples? You want to think of more? Or is that enough to go on with?
Do you have more examples?
Sorry?
Do you have more examples or something?
Well, I don't know if I want to suggest any more right now. It's not too many more that we've thought about. It starts to get pretty hard. What I can do, or what I do have to do, is this afternoon, we've been working with some research assistants on these questions, and they have come up with a program that does computer searches. So at 1 o'clock today, one of the research assistants is coming in and is going to demonstrate this. So perhaps we can think about more examples till there. But or you can think of some examples you'd like to test.
Okay.
Will it be online or?
I think what's going to happen is he's going to come here and run it on his laptop and
So-
share the screen.
Okay, yeah.
And then, yeah, if you want to make some suggestions of things to look at, then we can do that. All right. Is there anything else?
So would his program, would it like also take in one of these examples and try to create a graph from it, or what would it do?
Yeah, that's what it will do. It'll take one of these examples and try to extend it. So what we've done is we've tried to implement. So when we do things by hand, we're just trying to get the computer to do that. You know, try this, extend this way. Does that work? And that's it. And can we continue? And so for the hexagon, for example, it gives a tessellation of the plane, but it actually the last time we ran it took quite a while to do the hexagon. So
how does it go for, like, let's say the 3-dot line?
yeah,
Like, does it make a polygon? Does it infinitely extend?
no, it tells you can't find
Oh,
can't
Oh,
find
okay.
the conversion. So it runs trying to find an extension, and then if it runs out of options, then it says, well, no, there is no extension. So it can tell you if there is no extension, maybe, but if there is one, it doesn't stop. It doesn't stop and tell you, oh yes, there is one. It just keeps going. So all we can do is say, do this many steps, and then tell us the answer, and or tell us what comes out, and then we see that it continues that number of steps, and we see something. Now, one way we might be able to use that is to use the calculation to think about how it could continue to give us something.
Yeah, so
The computer can't tell us that it will continue forever, but we might be able to see that it can.
right, like it might tessellate some of it, and then you see how to, continue.
Yeah. So when we start to see a tessellation of the plane, well, we can see, oh yes, that will continue. But and the same with the 4 dots. Right? It tells you that it stops. We tell it to stop after a certain number of steps, and after that number of steps, you can see that it's starting to produce this band with the zigzag edges. But you can see there might be other questions to ask as well. So with the 4 dots, it extends to be some band with the zigzag. So it's somehow one-dimensional. It's only extending in one dimension. And that one actually you can wrap around and get a finite extension as well. With the 4 dotted line. But with the hexagon, it extends, but it extends in a plane, and we can't wrap it around to get a finite one. So there are more refined questions we can start to ask beyond just does it extend or not, but does it extend in some dimension? Maybe some of them have to extend in 3-dimensional, something like a 3-dimensional arrangement, or higher, and maybe some of them don't have any dimension. Well, the tree, the infinite tree, that doesn't sit naturally inside any finite dimensional space, because the number of points in a ball of radius n grows exponentially. Right, it's roughly 3 to the n in this case. But in a 3-dimensional space, for example, the number of points on the surface of a sphere grows quadratically. So we can't draw this naturally inside a 3-dimensional space or any other, or a space of any other dimension, because in any finite dimensional space, the number of points, if we spread points evenly on the sphere, that grows at a polynomial rate. Whereas the spheres here are growing exponentially. Yeah, so this one doesn't fit in any finite dimensional space. And I think that's got to be true for. I said that when we want a subgroup fixing a vertex to be infinite, I don't think any of those will actually fit in any finite dimensional space. Anyway, they are questions being answered soon. Anything more at the moment? Should we come back at 1 o'clock?
For the lesson.
Yeah.
Yeah. So we come back at 1.
Okay.
Yeah. Okay.
All right. So in the meantime, why don't you think about some of these questions we haven't answered, and if you answer those, maybe you can think of some questions yourself. Well, some other graphs. Well, what about those? How can we extend those? And then if you're doing that, you might come up with some questions that we want to run on the computer.
Yeah, seems fair.
Yep.
Okay. So we'll come back at 1, and then maybe in the afternoon we can look at that, and then maybe we'll have more questions after that, or also I might ask you to comment on my slides. What do you think?
Yeah, sure.
Yeah, sure.
Yeah. Okay. Well, I'll see you at 1 then, shall I?
See ya.
See you.
Yeah. Bye.
Stop recording.